My name is Amber Gillenwaters. In this presentation, I will summarize and provide an interpretation of a research article relating to scalable system scheduling for high-performance computing and big data. First, I'll review how these systems have evolved over the past couple of decades. Then I'll explain and show the methods that the researchers used and the outcomes. First, I want to acknowledge the researchers listed here from MIT, and I want to note that the purpose of this presentation is to educate and to meet the requirements of a graduate class. In 1965, Gordon Moore was an MIT graduate, and he was working in industry as a director of research and development. He saw that integrated circuits were doubling in the number of components they could contain about every year, and he predicted that this trend would continue and that this would bring about a proliferation of electronics, pushing the science into new areas. This prediction has held true. We saw the size of computers decrease and the capacities increase. So here we have the Osborne personal business computer from the early 1980s. Compare that to what we have now with smartphones. It's not uncommon to have a smartphone with 4 gigabytes or 8 gigabytes of RAM. This chart demonstrates that rise over the past 50 years in processing power. Notice the y-axis is logarithmic, so this is growing very fast. The rapid increases in processing power and new access to vast amounts of data has changed the face of our world. In this section, I will introduce this topic area in more detail, describe motivation, and what the researchers hope to show and to test. Scalable system scheduling here refers to job schedulers. Job schedulers are used to allocate resources and coordinate processes in parallel processing. With high-performance computing, generally jobs are submitted to a batch queue to be scheduled within minutes or days. Whereas with big data, these jobs are typically executed immediately. Most are brief, independent, time-critical jobs. In the recent past, job schedulers were primarily used to manage computations over, many days or weeks. But increasingly, big data architectures require many short calculations on large quantities of data. High-performance data analytics usually involve both high-performance computing and big data. In health, these technologies and techniques can be used in bioinformatics, genome sequencing, drug testing. In manufacturing, they can be used to reduce waste, improve safety. The applications are literally endless. More locally, Bluebird Network is a regional telecommunications company with a data center right here in Springfield, in the Springfield Underground, if you've heard of that. They peer with Netflix, with healthcare companies, cloud service providers, and government agencies. A job scheduler can be thought of as like an operating system for a data center. Scheduling is really complicated because there's multiple processing cores, you have many network links, all kinds of different memory stores, different storage pools. You have different items that need to have certain licenses. You have many users requesting tasks at a time, and each task may have its own execution paradigm that needs to be met. What makes up a job scheduler? A job scheduler is comprised of these basic component functions. So we have job lifecycle management, basically that takes in the jobs. We have resource management that organizes availability and gathers state information from the different nodes. Scheduling actually allocates the resources, and job execution actually carries those jobs out. And when those are done, it closes the job and collects information. This chart from the article compares job type with duration to kind of give you an idea of what these look like. The researchers in this article do an analysis comparing performance characteristics across 15 different systems, focusing primarily on latency, particularly in those short-term, quick turnaround jobs. They use a mathematical model that they define, explain, and then use it in testing and benchmarking the 4 most popular schedulers. Reducing latency at this scale can have a very big impact. For instance, the researchers point out that a 100 megawatt data center wasting only 1% of its computing cycles can nullify the equivalent of the energy saving measures of a small city. To put that into perspective, our Bluebird data center in Springfield is 1 megawatt, but some of these big ones really use a lot of energy. It's been suggested that every dollar invested in high performance computing returns on average more than $500 in revenue. So this is pretty big business. Next, I'll go over a brief history of early systems and early examples of benchmarking to support the classification that the researchers chose to do. You'll see that these early forms and current forms are closely related. One of the earliest examples of a scheduling system was developed by the United States Army at the Ballistic Research Laboratory at Aberdeen Proving Ground in Maryland, the MDQS. Pictured is Michael Moose, one of the researchers. It was presented at the USENIX conference in 1982. The Intel Hypercube was used in early development of supercomputing. The NQS was used by NASA on the machines shown in that previous slide. Here we have some early examples of benchmarking. On the upper right, we see a model a hypercube and show partitioning. So that would be an example of a 4-dimensional cube being partitioned into 3-dimensional cubes, a 3-dimensional cube and 2 2-dimensional squares. This academic, Dr. Gensch, was very influential in this area. He was an aerospace engineer. He started his own company and began developing what would become Grid Engine. In 1991, the World Wide Web was made available commercially, and so that made a huge difference in interconnectivity between systems. NASA researchers developed PBS, which replaced the NQS showed earlier, still on these same machines. It's actually still available under Open HPC. Also in 1991, a forum of academics and professionals in industry came together to collaborate together and release a standardized communication system. A team of academic researchers famous for developing the load sharing facility created a company called Platform Computing in 1992. Gridware was a merger between Chord Systems Inc. and Gensch's company shown earlier. He also had developed coding, which you may recognize. In the year 2000, Gridware was acquired by Sun Microsystems. In 2003, a group of student researchers published Slurm, which is funny because the name is based off of a Futurama soda. MapReduce was first described in 2004. It was based off the idea of map function and reduce function in programming. It uses key value pairs to process and to represent big data, and a small startup called Nutch implemented MapReduce in the same year. In 2006, Sun Microsystems released SunGrid, which was an early version of Grid Engine. Apache Hadoop was a side project, a spinoff from Nutch, mentioned earlier. 2007, Platform Computing released Platform Lava. In 2008, Yahoo bought Nutch, and that division, Nutch, became Hadoop. Hadoop, by the way, is named after one of the starting founders' child's toy elephant. So that's why it's called that. In 2008, Yahoo also came out with the fastest search of a terabyte. A system called Nexus was proposed by RadLab with Berkeley UC. They had a lot of big sponsors shown in the picture. They introduced it at Usenix 2009. Apache Nutch 1.0 was officially released in 2009. The Nexus project from 2009 ended up being called Mesos instead and was introduced in 2010. Also in 2010, Sun was acquired by Oracle, including that Grid Engine. In 2010, an open source version of Grid Engine was released based on earlier versions of it called Open Grid Engine. Univa ended up acquiring Grid Engine in 2011. In 2012, IBM bought out Platform Computing. In 2011, some former Platform Computing employees released OpenLava. This was later taken down by IBM, who claimed that it was an IBM property, that it was confidential and proprietary source code. Apache Hadoop Yarn was released in 2012. And Apache Mesos had been used for about 5 years by Twitter and other major companies, but it was released officially as Mesos 1.0 in 2016. In this section, I'll briefly describe their mathematical model. To begin with, the researchers considered two testing scenarios, basically. So in the first case, there's a low scheduler latency impact. In the second case, the latency impact makes a big difference. Because in data analysis, there's many short duration tasks, generally the latency impact is pretty high. As far as the procedure, the researchers followed Ruther et al. Using a fully isolated MIT SuperCloud cluster with 45 nodes. One of those was a scheduler. Only one scheduler being tested was running at a time. Each scheduler was configured for optimal performance on short duration jobs. The systems tested include the Son of Grid Engine, Mesos Single Node Master, and Apache Hadoop Yarn. This is the model proposed by the researchers to determine latency. So it involves these different factors: the number of tasks per processor, the time per processor, the uppercase P is all the processors, and then T of S is the marginal scheduler latency incurred whenever a task is added. And then the alpha is a exponential that accounts for non-linear behavior. And then there's total time, job time per processor, and the overall system utilization. The overhead is influenced by submission, by queue management, resource identification, resource selection, allocation, job dispatching, and job teardown. This is a visual they included showing end tasks and an execution of a job on a number of processors. This table summarizes the parameter sets and the runtimes used to measure the scheduler latency. Those lists of 3 numbers, those were 3 trials each in each of those different categories. So there's rapid tasks, fast, medium, and long tasks. In this section, I will briefly go over their results of their analysis. So this was the outcome for their model. We have the marginal latency. So Mesos and Hadoop Yarn had higher marginal latency. And then on the right-hand side, we have the alpha nonlinear exponent. So here we have a visual of their function with varying task times. So all the schedulers do pretty well with 1-minute tasks, and the schedulers launch jobs reasonably fast. Slurm, Grid Engine, and Mesos perform pretty similarly with 1, 5, and 30-second tasks. Hadoop Yarn was so slow that it couldn't even be used for part of the trials. It was quite inefficient. The researchers observed that all 4 of these systems had much lower utilization rates when it came to 1 and 5-second jobs. In their next step, the researchers employed multi-level scheduling to improve utilization, and they were able to do so to around 90%. With this technique, there are not as many jobs launched overall, so it allows processing of multiple data sets with just one execution. In the case of Slurm, there was a reduction of 30 times delta T at the largest values of N, comparing multi-level scheduling and then without multi-level scheduling. To conclude, I want to share my interpretation of the article. On the plus side, the authors successfully proposed a framework that will support further study. They isolated the factors involved, and they demonstrated methods that can improve testing and to improve efficiency in high-performance computing and in analyzing big data. And they show results using 4 primary schedulers. I didn't really see any flaws in what they did with what they had. As far as cons, and I think this may be more of future directions, but the paper is necessarily limited in scope. It's just difficult to test. Not everybody has a MIT cluster, and it's an emerging field. So obviously more research is needed, replicating, varying the configurations, the parameters, using additional schedulers, maybe some that are more recent. You probably noticed most of those are 5 or 6 years old at this point. And further reduction techniques, and on different systems, different applications, different types of jobs, different types of data, with different dimensionality. It seems to me with the map reduction algorithm, it clearly improved efficiency in short-term problems, but there's likely a more optimal solution than that. One thing I find inspiring is just how many of these products and projects that we've all seen originated from student researchers. So just students knocking around and coming up with something theoretical that was actually taken up by big tech and is used by people on a daily basis. So I think that's really neat, and I wasn't familiar with the history of these different resources that we kind of take for granted. Thank you for your time and attention. I will share my references with this video. Thank you again.